Welcome back, learners and circuit explorers. You've just tuned in to the latest episode in our electric adventure through Principles of Electric Circuits by Floyd and Buchla. This time, we're diving into RC circuits, a journey into the world of resistors and capacitors working together to shape time and voltage in a circuit. So, what's in store? How do capacitors and resistors create time delays? What's a time constant, and why is it at the heartbeat of so many systems? How do RC circuits charge, discharge, and respond to AC signals? You're going to see how RC circuits control more than just electrons. They manage timing, rhythm, and response, making them key players in audio filters, signal processing, pulse shaping, and more. Ready to decode time itself, one resistor and one capacitor at a time? This is it. The countdown starts now, and let's get into it. Before we tame time with resistors and capacitors, we need to talk about ghosts. That's right, not the kind that haunt old hospitals. Though I do love a good ghost hunting show, no, we're talking about complex numbers, those mysterious entities that live halfway between real and imaginary, much like the blurry figures caught on grainy night vision cameras. So, what is a complex number? It's a combination of a real part marching along the horizontal axis and an imaginary part climbing the vertical one. And together they form a point on what we call the complex plane. This is the secret map where phasors, those spinning vectors of voltage and current, live and move. You saw this first back in chapter 11. And here's a fun parallel. Imagine your multimeter is a ghost detector. It picks up voltage. It's real, it's measurable, but lurking just out of sight is the imaginary component, the phase, shifting everything a little off center. You can't see it directly, but oh, it's there and it matters. So when we analyze AC circuits, we're not just plotting numbers, we're ghost hunting in the complex plane. And trust me, the readings will make your hair stand on end, electrically speaking. Haunted angles of the complex plane. So tonight we rotate into the shadowy circle of angles and quadrants. Welcome back to Seekers of AC Circuits. We're now entering the phase dimension, the complex plane revisited. Previously, we set up our map. Now, we travel it. On this complex plane, angular positions tell us where a phasor, our voltage or current vector, is pointing at any moment in time. So start off at 0 degrees along the positive rho axis, move counterclockwise 90 degrees, that's straight up, into the positive J imaginary realm. Go further 180 degrees, that's across the void, back along the negative rho axis. Continuing to the 270 degrees down into the negative J shadows, and then coming back full circle to 360 degrees, back to where it all started. Each section is a quadrant, and everyone tells a different story of phase relationships. And here's a fun thought. Picture a paranormal investigation team reviewing camera footage. Suddenly, the compass needle spins. We got activity, says the host. Well, if you see your phaser swinging into the third quadrant, where both real and imaginary parts are negative, you know something's reverse polarity, not paranormal, but electrically suspicious. And why it matters? These angular positions help us track time shifts between voltage and current, like telling if the ghost showed up before or after the lights flickered. In RC circuits, this phasor rotation is the heart of the time delay, the phase shift, the reason why your signal doesn't arrive when you expect it to. And next up, we dive into the final slide of the series, how to write and use complex numbers to measure those very shifts. Say the word and we'll continue our spectral scan of the circuit world. Coordinates from the complex beyond. All right. So some of you who know me know I like to watch ghost shows, and it's not like I believe that everything they measure on those ghost shows are real. I mean, they measure things that are natural, not supernatural. Everything can be explained, but I do enjoy them using a lot of our devices, and making all these relations to ghost did this or said that. But anyway, welcome back, explorers of phasers and phenomenon. We've circled the plane, mapped the quadrants, and now we zero in on the exact coordinates of our spectral signals. We're plotting points on the complex plane. So in this chapter of our complex number saga, we ask, where exactly is our phasor? When a point floats free, not stuck on an axis, it's a complex number defined by two components. A real part measured on the horizontal axis, an imaginary part measured vertically on the J axis. And let's investigate some sightings. Right in quadrant one, where both real and imaginary are positive, we detect the presence at 7 plus J4. Over in quadrant 2, things turn spooky. The real value is -2, and the imaginary is plus J6. Look at quadrant 3, that's dark territory. -4 and -J1. Both components negative. Proceed with caution, like venturing into the basement after midnight. And then finally in quadrant 4, we've got 3 minus J8. Bright energy, but it's being pulled downward. Picture something trying to communicate from below. Ghost show reference? You bet. You know how they always say the spirit energy is strongest at the edges of the rooms. Well, here it's the edge of the real and imaginary axis, and if you really want to make contact, you have to plot exactly where the signal is strongest, just like this. And some final words from the field. In AC circuit analysis, these coordinates let us describe impedance, voltage, and current phasors in mathematical terms. No Ouija board required, just math. So next time your voltage swing is out of phase or your current vanishes into the imaginary, ask yourself, where is it on the plane? And is it trying to tell me something? Until next time, stay curious and always check your phase before flipping that switch. Value of J. Welcome back, frequency seekers. In today's segment, we step into a realm where numbers rotate, where values circle through dimensions, and where the humble J isn't just a letter, it's a portal. Rotation, not imagination. In the complex plane, multiplying by J rotates a vector 90 degrees counterclockwise. Not a step forward, not a jump up, but a full pivot in phase space. Think of it like turning to face a new direction without taking a single step. So if you start at 7 on the real axis, multiply by j once, and you're at j7. That's straight up. Multiply again, that's j squared, which gives you -1 if you remember your mathematics, and you make your mathematics teacher very, very proud. So then you're at that -7 full left. Multiply by j a third time. That's going to give you -j. That drops you downward to that -j7 direction. And one more time, multiplying by j gives you j to the fourth, and you're all the way back home to 7. Cue the X-Files theme, right? Ghost show vibes. If you've ever watched a spirit box spin dials across the static hoping to catch a voice, J is that dial. It rotates through unseen dimensions from real to imaginary to negative real to negative imaginary and back. A perfect loop, a cycle, and maybe just maybe a signal that's trying to reach you, right? The power of rotation? Yeah. So we'll go with that one. This rotation isn't just poetic, it's practical. So in AC analysis, multiplying by J lets us rotate phasors, solve differential equations as simple as algebra, visualize impedance, and make sense of signals that change in time. It's like having a compass, a decoder ring, and a ghost detector all in one. So closing off this transmission for this slide, next time you're deep in math and the valley starts spinning, don't panic. You're not being haunted, you're just on the complex plane, and J is your guide. Until next time, keep your circuits balanced and your vectors rotating. And cue the X-Files music one more time. Rectangular form. So, welcome back. In this segment, we shift from the rotating elegance of J to the precise grid of rectangular form, a foundational way to represent phasors in a complex number format. So, what is rectangular form? I can't believe you're asking me that after you've taken algebra or trig or pre-cal, but let's go ahead and talk about it anyway. Rectangular form expresses a complex number or a phasor as a sum of two parts. So you have the real component along the horizontal axis, you have the imaginary component scaled by j along the vertical axis. And we write it in the following, where it's a plus jb. And this is similar to how we broke down inductors into resistance and reactance, right? The real part was resistance, denoted by R, and the imaginary part was inductive reactance, and that was denoted by the JX. In this case, it was plus JX, right? Same structure, different component, right? But if we want to plot phasors, take a look at the plotted vector -4 plus J5. It starts at the origin and lands in the second quadrant. The -4 units along the real axis means goes to the left, and the +5 units up on the imaginary axis, it goes up. And here's the question for the screen. Where is +4 -J5 plotted? Right, kind of the opposite there. Think it through. So you move 4 to the right on the real axis and down 5 on the imaginary axis. And that lands us in the fourth quadrant. So from the second quadrant to the fourth quadrant by switching those signs. Uh, Diagonally opposite the original point, if you will. It's a mirror image with a twist, phase, and direction both matter in this case. Um, so when you analyze RC or RL circuits, we often shift between rectangular and polar forms. I mentioned why we do that before. Sometimes it's just easier to do mathematics in polar form and other mathematics in rectangular form. And we'll get into the details of that later. Rectangular is actually excellent for addition and subtraction, especially in series or parallel combinations, just like how you add inductive reactance and resistance on perpendicular axis. You'll do the same here. The rectangular form helps us see the structure of complex impedances or voltages before converting to polar for magnitude and phase angle. So let's do a quick recap here. Rectangular form is in the form of A plus JB. A is the real, that JB is the imaginary. You can graph it on the complex plane. A can go left or right, B can go up or down. Again, know your quadrants and your angles. Coming up next, we'll rotate the vector into polar form where magnitude and angle take the spotlight. Stay tuned. Polar form. So if rectangular form is the street address, polar form is the GPS. Welcome back. Today we're taking a fresh look at phasors, this time in their polar form, where every vector becomes a journey of magnitude and angle. Sometimes I feel like William Shatner. Welcome back to today. Anyway, forget it. That was a really bad impression. So, what is polar form? Polar form describes a phasor using c, the magnitude or the length of the vector, theta, the angle measured counterclockwise from the positive real axis, and we write it as follows, as you see on the slide: c at an angle of plus or minus theta. And this tells us not just where the vector ends up, but how far and in what direction it travels. This is perfect for AC analysis, especially in sinusoidal steady state circuits. So let's look at the example from the slide. Take the phasor 6.4 at an angle of 129. What does this mean, right? It means that you start at the origin, you move out 6.4 units, and you rotate 129 degrees counterclockwise from the positive real axis. You'll land solidly in the second quadrant where the red arrow points. Now here's your challenge. Where is 6.3 at an angle of negative 72? Where is that plotted? And the answer is, again, move out 6.3 units and then rotate clockwise, since it's a negative 72, from the real axis. And again, you'll land, in this case, in the fourth quadrant. That's right. This complements the rectangular form from the slide where we looked at plus 4 minus J5 that landed in that same quadrant. Different language, same location. And why do we use polar form? Well, polar form is ideal for multiplying or dividing phasors. Working with impedance and current voltage ratios, visualizing phase differences, especially in RC and RL circuits. It's also the go-to format for interpreting magnitude and phase response in filters. Compare it with inductors. In RL circuits, inductive reactance gives us positive JX, and RC circuits, capacitive reactance gives us negative JX, and the resulting current leads the voltage. These angles matter, and polar form captures them directly. So let's do a quick recap. Use rectangular for addition subtraction. Use polar for multiplication division and angular analysis. Angle direction defines a phasor orientation. Combine forms when you need to for full control of phasor algebra. And again, up next, we're going to connect all this to things like Ohm's law in the complex plane. Complex plane. Some of these words are not easy to say for me. Uh, Keep your vector sharp. See you on the next curve. Converting rectangular to polar form. Hey, welcome back. If you've ever tried plotting a ghost on a map, you need two things: how far and in what direction. And don't worry, no spirit talk here today, just phasers. I'm done with that ghost stuff for this podcast. Yeah, got over it. So converting between rectangular and polar forms. In the last slide, we saw how rectangular and polar forms are two sides of the same vector coin. Today we unlock the math that lets us switch between them using simple, don't freak out, trigonometry. That's right. So from this triangle, we get everything we need to move between coordinate forms. So we look at sine, where sine theta is equal to opposite over hypotenuse, and then cosine, where cosine theta is equal to adjacent over hypotenuse. And we use the function for tangent theta is equal to opposite over adjacent. And of course, don't forget Pythagorean's theorem, where hypotenuse squared is equal to the adjacent side squared plus the opposite side squared. And this triangle represents a phasor vector, just like the one we used in earlier slides with inductors and capacitors. So from rectangular to polar, so you have a phasor written as A plus JB, where A is the real component and B is the imaginary component. If you want to convert that to polar form, first you need to find the magnitude. And the magnitude can, because we're looking at Pythagorean's theorem, would be C is equal to A squared plus B squared. I'm sorry, C is equal to the square root of A squared plus B squared. If you want to find the theta, the angle, theta is equal to the inverse tangent of B over A. Uh, so you can express the phasor in polar form also, where you have C at some angle theta. And this lets you perform operations like multiplication and division more efficiently. So from polar back to rectangular, you reverse the process where A is equal to C cosine theta, B is equal to C sine theta, and then write it as A plus JB. It's exactly what we did when analyzing current and voltage in RL circuits earlier in our podcasts. Especially when calculating power triangles or understanding phase shifts, if you remember that. So this matters in RC circuits because in real circuits, whether it's inductive or capacitive, phasor math lets us solve Ohm's law in AC. Remember the V is equal to I times Z, where Z could be complex and Z is the impedance, if you don't remember. Being able to bounce between rectangular and polar form lets you plug into formulas, do your math, interpret both magnitude and phase directly. Allows for critical understanding of filter behavior, timing, resonance, and so forth. All right, so let's go ahead and wrap up this slide. Trig gives us the tools to translate between two forms of the same signal. Pythagorean theorem, or the Pythagorean identity, ensures accurate magnitude. Tangent tells us the angle. The direction of our phasors, I said I wouldn't do this anymore, but our phasors ghostly glow. And we'll use these conversions in analyzing impedance and phase relationships. And that's it for this slide. Keep your vectors aligned and your calculators charged. We're just warming up. Version from rectangular to polar form. Welcome back. If you've just tuned in, we're walking the bridge between rectangular and polar forms, a journey every signal takes when passing through the AC circuit analysis. Last time we learned the foundation of this conversion using basic trig functions. Now let's put that into action. So let's look at the slide. The math behind the transformation. We're going to convert the complex number negative 5.0 plus j 3.3. And this number lives in the second quadrant. And how do we know this? Because it has a negative real part, the negative 5.0, and a positive imaginary part, the plus 3.3. So the first thing you want to do is calculate the magnitude C. So to get the vector's magnitude, we use the Pythagorean theorem, where C is equal to the square root of A squared plus B squared. Plugging in the numbers, we get, what do they show there? It's hard to read, 5.99. And this tells us how long our phasor is. A direct analog to how we described impedance vectors way back in RL circuits. Right. Step 2, you want to calculate the angle. And this is where direction comes in. We use tangent for this. So theta is equal to the inverse tangent of B over A, and you see that on the slide, and they come up with 147 degrees. The final polar form of the phasor then becomes 5.99, which is the magnitude at an angle of 147 degrees. Right? Let's go ahead and connect this back to RC circuits. Why does it matter? Well, imagine you're analyzing a capacitor's impedance. Its value in rectangular form might be tricky to plug into a voltage divider, but in polar form, it's all about magnitude and phase, and that's what your circuit cares about. It's like tuning a paranormal antenna. I promised you I wouldn't say the paranormal or ghost things anymore, just a few slipped out here. So if you know the distance or the magnitude and the direction or the angle, you can perfectly align the signal. Capacitive and inductive reactances, they behave like this all the time. A little different between what you may have learned in your mathematics class and your engineering classes, that we actually put that mathematics to practical use. So here, that math means something direct that you're going to be using. So let's use this form when multiplying or dividing phasors, and then the rectangular form when adding or subtracting. Again, multiplying and dividing is when you want to use the polar form, and then adding and subtracting is when you want to use the rectangular form. Next up, we're going to look at plotting these conversions visually. And yes, we're still avoiding any ghost signals. Haha. Stay tuned. I said before, this is not a calculator class, and nor am I promoting one particular calculator over another, but we have instructions for the TI-84 on this slide from this publisher. So let's go ahead and look at the slide and look at how we convert from rectangular to polar using your calculator. So the last segment, we took a long road, manually calculating the magnitude and the angle of the complex number, negative 5.0 plus j 3.3. But let's face it, in the lab or even during an exam, you won't always want to wrestle with trig identities. So that's where the scientific calculator becomes your best friend, or your, I would just leave it as your best friend, right? And so today's tools, the publisher illustrates the TI-84 plus CE. We're going to look at the calculator shortcut for doing this. So we're going to look at how to go from rectangular to polar. So to access the conversion tools, press that second key function, then press apps to open the angle menu. Use option 5 to go from rectangular to polar for the magnitude, PR, and then use option 6 to go from rectangular to the angle, to find the angle. And then type in your rectangular coordinates just as they appear, right? Negative 5, comma 3.3, and that's supposed to be the values for the rectangular. And then you're going to see the magnitude, 5.99, and angle, 146.57 degrees. And the slight difference from our earlier result of 147 is that the calculator is being a little more precise with the decimals, but fundamentally the answers, they check out. And why does this matter for, let's say, RC circuits? So if you remember, in an RC circuit, capacitive reactance introduces a phase shift. So when you're solving AC problems, converting impedance or current values to polar forms, it makes it easier to multiply, divide, and understand those phase relationships. So instead of mapping every single triangle manually, a few calculator keystrokes lets you model that phasor voltage drop across the capacitor instantly. So this kind of thinking is efficient, clean, and analytically aware. It's exactly how we approach the math in the inductor podcast. Going from polar form to control over both magnitude and time delay, um, you can do this easy with your calculator. I may do some videos separate from this later on with the HP48 or HP49 calculator, one of my favorite calculators. Again, I'm not promoting any calculator, but if we don't have instructions on how to use those, I'll create some videos for that. But that's beside the point. Coming up next, in the next slide, we're going to demystify the idea of multiplying complex numbers and how this affects magnitude and angle. And spoiler, it's like putting your signal on a turntable and giving it a spin. So stay sharp and keep your calculator close. From polar to rectangular form. Welcome back to the podcast. We've just looked at how to convert from rectangular to polar form. Now let's take the return trip converting from polar to rectangular form. And why does this matter? Well, whether you're modeling a voltage across a capacitor or calculating current in an RC or in an RL circuit, sometimes polar form just isn't enough. You need the real and you need the imaginary components literally. And here's the formula breakdown. So if you're given something in polar form, and let's say you have 12 at an angle of 45, you can translate that into rectangular coordinates using the formulas. A is equal to C cosine theta, and B is equal to C sine theta. It's right up there on the slide. Just like we did with the impedance back in the inductor podcast when we talked about that, where we had inductive reactance, which was Jx sub L, and the imaginary component, which would have been the X sub L. That vertical axis, remember, was all imaginary, just like here. So the example that we got is, and let's run these numbers, or plug and chug, right? A is equal to 12 cosine 45, and that gives us 8.49. and B, again, equal to 12 sine 40, excuse me, 12 sine 45. That also gives 8.49. Something very special about the angle 45 being right in the middle, letting us know that both legs of that triangle are equal. So those numbers should be the same. So your rectangular form is going to be 8.49 plus J 8.49. So that's, yeah, when you're dealing with the angle 45, that's one of those special cases where you see both the real and the imaginary part having the same length. So again, if you see this in rectangular form, I can already tell you that's 45 degrees. So it's nice, it's symmetric. The phaser lands right in the first quadrant with equal parts real and imaginary. That's the interesting thing about the 45-degree turn off the positive row axis. And why is this useful in RC circuits? Sometimes you'll know a capacitor's voltage is swinging at a certain angle and amplitude, like in polar form, but your analysis, say for like nodal voltage or phasor addition, needs those A plus JB components, right? The real plus imaginary components. And that's where this conversion comes in handy. So as we've said before, being able to go back and forth between forms like this gives you fluency in that second language of mathematics. It's not just being smart, it's actually very, very necessary for us engineers. In the following slides, we're going to actually test this process using the calculator. If you thought trigonometry was just high school nostalgia, surprise, surprise, it's still earning its keep here. In fact, it's very, very essential. So stay tuned and sharpen your angle menus. In not a calculator promotion video, but again, because of the slides, we're going to look at the TI-84 plus CE and how to do this conversion. So if we want to convert from polar to rectangular, right, let's do some math to get this thing into motion, literally, using that TI-84 plus CE calculator. And I'm sure you can do this with other calculators of the same type, right? So last time we converted the phasor 12 at an angle of 45 manually into rectangular form. Now we're going to go to check those results digitally by just punching in the numbers in the calculator and using the functions. So let's look at the calculator instructions step by step. So first, access the angle menu by pressing the second key function. Go to apps, and that opens the door to options for working with angles. Go to polar forms and trigonometric utilities. Now here's what you're looking for. You can press the seventh option, which is going from polar to rectangular, which will give you the X component, and then press 8, which goes from polar to rectangular to give you the Y, the imaginary component. Then just simply enter the polar values in the format. The magnitude, comma, angle. So in this case, 12, comma, 45. Press enter and voila, you get it. A is 8.485 and B is 8.485. Now, again, because it's an angle 45, I know that the legs of the triangle are going to be the same magnitude. So A and B being equal, I'm expecting that. And this just confirms exactly what we calculated by hand on that previous slide, where we had 8.49 plus J 8.49. So what's the point of all this? Well, here's where things connect. Remember how we dealt with phasors in the RL circuits. You might have been handed a voltage or a current in polar form, especially when using impedance analysis. But to analyze voltages in parallel branches or to solve for time domain response, you need to add those vectors in rectangular form. So you can see why we need to be changing from polar to rectangular, or a reason to be changing from um, sorry, polar to rectangular or rectangular to polar. So you can use your calculator to verify transformations. It helps you cut down on errors. It helps you save time, so you don't slip up and make some arithmetic error, right? And one good takeaway here is that your calculator isn't just some gadget. A long, long time ago, we were discouraged from using calculators. Now we're actually teaching you how to use that thing. So enjoy it. Uh, it's long overdue. Anyway, it's not just a gadget, right? The calculator. It's a phaser hunting sidekick, if you want to think of it like that. So once you understand the trigonometry, wow, I often mispronounce words, and that's a really good way to mispronounce trigonometry. Trigonometry. Uh, Tools like your TI calculator. I don't even think I want to mention models anymore, but these things they're not lost in the math, especially when you're deep in the signal maze of capacitors and inductors. So again, for us engineers, when you're deep in the practical use of this mathematics. So again, stay tuned for the next slide, and we're going to look at complex impedance, and we're going to start seeing how these forms really power up in practical circuits. Okay, mathematical operations with complex numbers. So this is where our complex number story starts getting interactive. You've seen how we convert between rectangular and polar forms, but what do we actually do with those numbers once we got them? Well, just like one more time, just like ghosts don't cross into the light without a reason, we don't manipulate phasors unless we're solving something important. So let's go ahead and break down addition in rectangular form. And the process here, we're going to talk about it step by step. So when you're working with complex numbers like the 8.48 plus J 8.46, um, and we're looking at that 6.20 minus J 5.70, you treat them like vector components. So you add the real parts and you add the imaginary parts. The real parts are the 8.48 and the 620. Go ahead and add those together, and that gives you 14.68. Then you add the imaginary parts, and don't forget to take into account the sign. So we have 8.46 minus 5.70, and that gives us 2.76 for the imaginary. So the result is for the real is 14.68, and for the imaginary, we have a sum of positive J 2.76. And so this is just like adding phasors in a series RC or RL circuit where voltages or currents are out of phase. Uh, you align the real with real and the imaginary with imaginary. And when you're analyzing voltages across components like resistors and capacitors and AC circuits, phasors allow you to solve for net voltages or currents pretty quickly. But to do that, your phasors need to be in rectangular form so that you can easily add or subtract. You saw how easy that was, right? This mirrors what we did in the inductor model where we treated the real and the imaginary parts as legs of the impedance triangle. But here we're just adding those triangles just like in a flat rectangular space. Here's a quick tip. Your calculator can handle this directly, but if you're in complex mode, just type the two expressions and hit enter, and the magic happens one step at a time. But I do recommend doing some math in your head. Keep your brain sharp and don't do everything on the calculator. Even like if it's simple, really try to do it in your head. Keep your neurons firing. Um, anyway, the takeaway here is think of complex addition as building your phasor toolbox. You're not just plugging in numbers, you're aligning waveforms, understanding phase relationships. You're preparing to unlock circuit behavior across time and frequency. Okay? All right. So thank you very much. Until then, stay curious and stay complex if you're adding or subtracting. Talk about mathematical operations. Now we're talking about subtraction. Not different from addition, right? Uh, So, welcome back, learners. So, you know how many times I do these recordings and I mess up and I redo them over and over? It may sound like it's smooth, but sometimes I do these many, many times, and it's like I almost memorize what I wanted to say. So, welcome back, learners. We're continuing our hands-on walkthrough with complex numbers. And today we're talking about subtraction, the mirror image of what we did last time. And so subtraction, again, real and imaginary paths. So let's go ahead and subtract what we see up there on the slide. 6.20 minus J 5.70. We're going to subtract that from 8.48 plus J 8.48. So pay attention to that word from, right? So you know what's being subtracted from. I mean, what's being subtracted from what? Uh, we have the real parts, 8.48 minus 6.20. And again, it's good to kind of line it up the way you learn addition and subtraction in the K through 5 or your elementary school days. Right? So when we add the real parts, we end up with 2.28. And then we do the imaginary parts, J 8.46 minus J 5.70. So remember, we're subtracting uh, the first complex number by the second complex number. So I'm sorry, I said that incorrectly. We're subtracting the first complex number from the second complex number. So that's why the second complex number is up on top. So J 8.46 minus J 5.70, and we end up with J 14.16. So remember this is subtraction. So J8.46 minus a minus J.570, that's going to give us the addition of J14.16. And then we put it together and we get the 2.28 plus J14.16. Again, you're determining the net voltage or current when one signal is counteracting another. This is where it makes practical sense for us engineers when we look at this math and why we do the math. It's like removing the reactive effect of one capacitor in an RC circuit. So why this matters in RC circuits, remember that when we subtracted the RL circuits lesson, um, we were modeling voltage drops across components. Same idea here. When signals oppose each other, whether across resistors, capacitors, or like in a feedback loop, you subtract their contributions. And again, yes, your calculator can help, but I really recommend you can do this in your head. You can do this on paper. It's not that big of a thing. Um, so there's some things you really shouldn't use your calculator for. Challenge your mind to do some mathematics in your head. Just plug in. You can plug in each of the complex numbers in your calculator, put it in the right mode, and boom, it gives you the right answer. But you know what? You can do this math in your head too. So do it in your head. And here's a tech tip. If you're thinking, isn't this just algebra? It is, but it's phasor algebra. That means it reflects phase, amplitude, and signal interaction all at once. So in RC circuits, going back if RC circuits had a ghost story, this is where one signal tries to haunt the other and get subtracted out. And let's wrap up this slide here. So whether you're adding or subtracting, rectangular form gives you the cleanest path to analyze signal behavior. It's not that you can't do it the other way in polar, it's just super messy. And then same thing, if you're trying to, I'll leave it there. I'll leave it there. Wait till we get to polar. So again, you're not just solving, you're modeling real world electrical reactions. Okay, so I think that's it for this slide. All right. We're going to talk about the polar magic next. So see you then. And remember, when in doubt, break it into real and imaginary J. Mathematical operations, slide 3 of 4. We're going to talk about multiplication. So again, welcome back to our deep dive into complex numbers and their operations. And we're turning up the voltage figuratively with multiplication in polar form. So why polar form? Because it rocks for multiplication. And here's the situation. Let's say you have two phasors, not the Star Trek kind of phasors, but mathematical phasors. And one of them is 8.30 at an angle of 25 degrees, and the other one is 12 at an angle of negative 15 degrees. If we multiply them in polar form, we do something very beautiful and very simple. And the key to this is to multiply the magnitudes and add the angles. So the magnitudes in this case are the 8.30 and the 12. So we can multiply those two together and we end up with the value of 99.6. The angles here are 25 and negative 15. So we can add those together. 25 plus minus 15 gives us 10 degrees. And so we end up with the final result of 99.6 magnitude at an angle of 10 degrees. And that's it. You're scaling the size and rotation, the direction, just like turning a volume knob and shifting the dial. In circuit terms, if you've ever worked with AC voltage sources and phasors in RC and RL circuits, prior to this, or you will after this, you've seen this play out. Multiplying phasor models, it's like gain changes or signal mixing or combining effects of multiple stages in the filter. It's one of those moments where math becomes a control panel. You can twist the magnitude, rotate the phase, and shape the waveform. So if you're trying to do some signal conditioning on a script, on a program, knowing the mathematics behind it will allow you to write a program to actually do the thing that maybe you could do in hardware. Right? So with inductors, if we remember when we did this with RL circuits, the same math, same rules. The difference is just what's reacting. So L for inductors, and we did C for capacitors, right? Um, Inductors store and delay current with that phase shift. Multiplying complex numbers in polar form helps us understand how those phase shifts interact across different stages in the circuit. And here's another calculator note. Your TI-84, again, still has your back. You can enter polar values and multiply directly. think of it again as having your own circuit lab assistant, but without the attitude. All right, so let's wrap this up because I've been jabbering too long. When you're working with multiplication and AC analysis, stick with polar form. It's quick. The visual is easy to see. It directly reflects the way signals interact in real world electronics. Again, I have a problem saying real world electronics. Um, that's it. Let's go ahead and talk about division in polar form. Right? You thought multiplication was exciting. Division is just as exciting. Mathematical operations division. So welcome back. In this segment on mathematical operations with complex numbers, we're tackling a deceptively simple concept, division in polar form. And division encompasses subtracting angles and scaling magnitudes. So let's set up a real example from this slide, or an example from this slide. So if you've got uh, a phasor at 8.30 at an angle of 25 degrees, and you want to divide it by 12 at an angle of negative 15 degrees, here's the beautiful part. Polar division works just like multiplication, but instead of adding angles, we subtract them. So we can divide the magnitudes 8.30 divided by 12, which gives us 0.692, and then we just subtract the angles. 25 minus a minus 15 degrees, which gives us 40 degrees. And the final result ends up being 0.692 at an angle of 40 degrees. This is simple, it's elegant, and totally aligned with how we interpret rotation in phasor space. What it means for RC circuits is that in RC circuits, especially when dealing with voltage division or impedance ratios, the operation comes up quite a bit. And when one signal is out of phase with another, or one magnitude is attenuated, and that's a new word, attenuated by a filter, this kind of operation tells us exactly how those relationships look on the phasor diagram. So think of it this way. Multiplication builds energy, like a capacitor charging, and division dampens it, like energy diffusing through a resistor. And here's a tip. Complex division feels like balancing scales. You're shrinking the signal's amplitude and you're rotating its angle. So it's like tuning a signal down and then shifting its timing. If you're a visual learner, imagine shrinking a spotlight and pointing it slightly to the right. It's still visible, just smaller and it's offset. Again, calculator friendly. You can do this on your calculator, no matter which scientific or engineering graphing calculator you have. Let's go ahead and close off this slide with this thought. You now have a full toolkit to add, subtract, multiply, divide, and whether you're in rectangular or polar form, your math follows the physics. Next, we're going to bring all this together and we're going to analyze complete AC circuits with phasor diagrams. I'll see you then. Keep calculating with confidence. Sinusoidal response of series RC circuits. So, welcome back, listeners. In this segment, we're cracking open a concept that bridges reactance and timing, the sinusoidal response of series RC circuits. So we have resistance plus capacitance, and that gives us some phase angle shift. And so here is the scoop. When you wire a resistor and a capacitor in a series, or in series, and I was going to say in a series circuit, when apply a sine wave, the circuit responds in a uniquely smooth way. So the current leads the applied voltage, but it doesn't go to the full 90 degrees like a pure capacitor would. Instead, the phase angle lands somewhere between 0 and 90 degrees. So let me go ahead and paint this picture for you. The resistor voltage V sub R, or VR, is in phase with the current, and the capacitor voltage V sub C, or VC, is behind the current. The total voltage Vs, the source voltage, is the vector sum of both. It's a subtle tug of war between the resistive and the capacitive sides of the force. May the force be with you. Yes, I had to say it. So compare it to the series RL circuit. Back when we discussed series RL circuits, remember how the inductor made the current lag voltage? Well, now the capacitor flips the story. The current leads voltage. It's a mirror image of the inductive phase shift. So instead of holding the current back, capacitance lets it run ahead. On your oscilloscope, you'd spot a current waveform peaking before the voltage waveform. V sub C slightly behind V sub S, and VR aligned with the current. And this phase relationship it's a diagnostic fingerprint, and it's how you know you have capacitance that's in play within the circuit. But how much phase shift, right? It depends on the ratio. The amount of lead depends on the relative values of R and X sub C, and that's right, the capacitive reactance X sub C being equal to 1 over 2 pi FC. Plays a big role here. If the resistor dominates, you have a small phase shift. If the capacitor dominates, phase shift approaches 90 or closer to 90. And it's like tuning the dial on a frequency sensitive dimmer switch. And there's a real world tie-in, and you know, I have a hard time saying real world tie-in. This is the behavior behind audio tone circuits, timing delays, and even crystal oscillator stabilization. Every filter from a guitar pedal. My son plays guitar. He has tons and tons of guitar pedals, and he's learning all the engineering behind that. I wish it was an actual audio engineering degree that was engineering based that he could get because he loves this. Anyway, uh, going from like a guitar pedal to a biomedical EEG, and most of you already know I'm a clinical engineer, so that's my passion. So if you're looking at any of those preamps, these rely on timing distance between the voltage and the current. And let's go ahead and wrap up this slide with one final thought. The series RC circuit doesn't just pass voltage, it shapes it with a bit of phasor math. So you can predict what shaping happens down to the degree. And next, we're going to go ahead and explore how these phase shifts map onto impedance and, yes, admittance. Think of it as plotting your circuit's personality in a complex plane. I teach psychology and I teach communication, so I love making these analogies to the social science and behavioral sciences. I can go on and on about the mathematics of waves of people operating very similar to these circuits. But that'll be for another time. But until then, just stay curious and keep charging up those circuits. Impedance triangle. Hello again, learners and circuit sleuths. We're entering the land of triangles, but not the Bermuda, the impedance triangle. Let's decode the geometry of how resistors and capacitors shape electrical behaviors in series RC circuits. So what is impedance in a series RC circuit? So in a series RC circuit, impedance isn't just resistance, it's the vector sum of R, which is the resistance plotted horizontally, and negative JX sub C, the capacitive reactance, and that's plotted downward on the imaginary axis. This gives us a right triangle in the complex plane. So we can visualize a triangle like this. Imagine the base of the triangle is R, the vertical leg is X sub C, but it points down because capacitive reactance is negative imaginary. The hypotenuse is Z, the total impedance, and this triangle is more than just a shape. It tells you the magnitude of the impedance and the phase angle between the voltage and the current. Now I said imagine. Imagine if you're just listening to this, but you don't have to imagine because it's right there on the slide. Um, so let's talk about the phase angle and how much lead. So the angle theta in this triangle is given by theta is equal to the inverse tangent of x sub c over r. So that capacitive reactance divided by resistance. Because x sub c is negative, theta ends up being negative. And this tells us what? That the current leads the voltage. That's a signature move of capacitance. Compare that to inductors. If you've been following along, this triangle might feel familiar. In an RL circuit, the inductors plus plus JX sub L phasor, that went upward, and the current lagged. Here in the RC world, the phasor points downward, and the current leads. So it's a visual mirror of a kind of B-side of the inductor story. So a negative B-side of the inductor story. Why shift the triangle? The slide shows how we can reposition the phasor vectors into this tidy triangle. And we call this the impedance triangle. It simplifies calculations and visual reasoning. So you can use a triangle to find impedance magnitude using the Pythagorean theorem, determine phase angle pretty easily, and then solve for any unknown using basic trigonometry. So this is how we can visually see the mathematics. But again, we know in the practical world for engineers, this actually applies to some real life components and how things are actually reacting, right? So let's go ahead and wrap up this slide. The impedance triangle is your circuit's phasor roadmap. We mentioned the roadmap before. It tells you everything you need to know about how signals behave in a resistive, capacitive environment. And that's it. We're going to dive into calculating impedance in real world circuits. So go ahead and grab your calculator, hold on to your unit circle, and meet me on the other side. That was a ghost pun. Impedance triangle in action, part 2. So welcome back. This time we're stepping into the practical side of phasor geometry. You've seen the impedance triangle in theory, and now let's plug in some numbers and watch it come alive. So the given, R is equal to 1.2 kilo ohms, and the capacitive reactance is 960 ohms. Let's go ahead and sketch the triangle, and they sketch it for you here, so just follow along. The base, which is the adjacent side, R is equal to 1.2 kilo ohms. The height, which is the opposite side, x sub c, that's equal to 960 ohms. But since it's capacitive, we treat it as negative 960 ohms. And this triangle is tilted downward as expected for an RC circuit, just like the one we introduced in the previous part. So step 1, find the impedance magnitude. You can use Pythagorean theorem again. Z is equal to the square root of 1.2 kilo ohms squared plus 0.96 kilo ohms squared. And that gives us, as you can see on the slide, 1.54 kilo ohms. Step 2, you want to find the phase angle. So theta is equal to the inverse tangent of negative 0.96 kilo ohms divided by 1.2 kilo ohms. And they give you, or they come up with the number negative 38.7 degrees. That negative sign is the giveaway. Current leads voltage. So this agrees with what we expect from a capacitor in series with a resistor. And this matters because when you're designing or troubleshooting RC circuits, this triangle tells you how much opposition or impedance the source sees. It reveals how out of phase current and voltage will be. So it lets you predict behavior without hooking up a scope and or predicting, and yeah, so it just kind of lets you know what's going to happen. So it's exactly how we approach inductors, but remember that with inductors, the reactance triangle went up and the current lagged, but for capacitors, it's downward and the current leads. I'm repeating myself over and over again, but I'm hoping that this will eventually stick if you forgot it. So repetition helps. So the impedance triangle, if we recap everything here, the horizontal leg is the resistance. It's always going to be. The vertical leg is going to be capacitive reactance, and this time it's going in the negative direction. The hypotenuse is the total impedance, right? The angle is going to be the phase relationship between the two. So Z is going to be equal to 1.54 kilo ohms at an angle of negative 38.7 degrees. And that's the final answer, both geometrically and electrically. And that's the interesting thing that I like, is that this is not just an answer of mathematics, and this actually means something for us in engineering. So I'll stop there before I ramble on. So keep that triangle in your toolkit, because next we're going to look at voltage and current phasors in series RC circuits. Until then, stay charged. Using phasor Ohm's law in series RC circuits is the title to this slide. Welcome back to our exploration of series RC circuits. You've seen the impedance triangle. Now we're ready to apply it with phasor Ohm's law. And this is your moment of connection where voltage, current, and impedance start talking to each other in phasor form. So the big three, Z, which is impedance, V, and I. Right? In a series circuit, current, I, denoted by I, is the same throughout all components. And that doesn't change from what we learned in the previous courses in DC circuits, right? So that consistency makes things wonderfully predictable. So here's how we use Ohm's law with phasors. So V is equal to I times Z, where voltage is current times impedance. I is equal to V divided by Z, where current is voltage divided by impedance. And Z is equal to V divided by I, where impedance is voltage over current. This isn't new. It's just Ohm's law upgraded. Ohm's law 2.0 to work with complex numbers and phase angles. And why use phasor form? So imagine trying to analyze a waveform that's always changing. Phasers just make it easier by capturing the peak behavior, the magnitude and phase in a very simple, single, clean arrow, right? It freezes the time so we can do math on alternating currents. In the RC series circuit, once you know the impedance of a triangle, the Z and the angle theta, and the current denoted by I, you can calculate each voltage. So across the resistor, V sub R is equal to I times R, which is in phase with the current. Across the capacitor, V sub C is equal to I times X sub C, but it lags the current by 90 degrees. And these voltages are phasors too. So together, they vector sum the source voltage. And the connection to the inductor lessons, you remember when we analyzed RL circuits. Um, Real quick, I was told a long time ago in educational science that when an instructor makes a little blurb or a mistake or something, to keep it in recordings because students like to hear the natural, way of just what we go through. So I'm leaving all that in there. So again, remember, when we analyze those RL circuits, sometimes I have to speak too slower. The strategy here is it's almost identical. The only major change is the direction of the reactance. So inductors, where we had the plus Jx sub L, current lags. Capacitors, where we have negative Jx sub C, the current leads. The math engine is the same. The only shift is the sign of the reactance and which waveform gets ahead of the other. That's it for this slide. So next up, we're going to talk about voltage, phasors, and action. You've got your equations down. We're going to put them to work in some examples, and we're going to do some calculations. So keep your phasors straight and your angles sharp. I'll catch you on the next segment. Stay curious, stay complex. Voltage phasors from impedance triangles. So welcome back, explorers of electric rhythm. In this previous segment, we built our impedance triangle for a series RC circuit. Now let's bring it to life using voltage phasors. So we're given a 10 milliamp current, and let's go ahead and revisit those values. We had a resistance of R is equal to 1.2 kilo ohms, capacitive reactance, they gave us that as X sub C is equal to 960 ohms, and the total impedance magnitude was Z is equal to 1.54 kilo ohms at an angle of negative 38.7 degrees. And if we apply the current at 10 milliamps RMS, we can find the other phasors. So all we got to do is multiply impedance phasors by current. Right? So using the phasor form for Ohm's law, V is equal to I times Z, we apply this individually to each of those components. So voltage across the resistor, I times R, that's going to be 10 milliamps times 1.2 kilo ohms, and we get 12 volts. V sub C, the voltage across the capacitor, that's going to be, same current times X sub C, or the capacitive reactance. So 10 milliamps times 960 ohms, that's 9.6 volts. And these values represent the phasor links for the resistor and capacitor voltage drops. That was step one. Step two is to sketch the voltage triangle. So we can use the same triangle shape from our impedance triangle, but scale the sides to voltage. So V sub R lies on the real horizontal axis, and that's in phase with the current. V sub C lies on the negative imaginary axis, 90 degrees behind the current, and the source voltage V sub S is the vector sum. And the V sub S is 15.4 volts at an angle of negative 38.7 degrees. And this confirms our system. The total voltage leads the capacitor voltage and lags the current. This reflects how capacitor pushes the current ahead. Compare this to the RL circuits. This is always good to do some comparison, compare and contrast. Here's the symmetry. So in RL circuits, current lags behind the voltage due to the inductor. In RC circuits, current leads the voltage due to the capacitor. But in both cases, the impedance triangle helps us predict the waveform relationships. And Ohm's law, or the phasor form of Ohm's law, translates triangle geometry into real-world voltages. And this matters because voltage phasors gives us precise control in AC circuit analysis. This is especially critical in signal filtering, timing circuits, and impedance matching, all the areas where RC behavior dominates. Voltage is no longer abstract, it's directional, dynamic, it's predictable. And that's it. We're going to go ahead and shift our focus next to frequency response. But until then, stay balanced and let your phasors fly. Oh, Put phasers on stun. Son of a gun. That was better. Anyway, too late. Frequency and the shifting triangle. So welcome back, Signal Sleuths. In this episode, we're tuning into one of the most revealing behaviors of an RC circuit, how frequency affects phase angle, and why this really matters. So capacitive reactance, we know, depends on frequency. And let's start off with a truth of the heart of it all for RC circuits. X sub C, right, is equal to 1 over 2 pi FC, which is 2 times pi times frequency times capacitance. And this tells us that as frequency F increases, the capacitive reactance X sub C decreases. And when X sub C shrinks, the shape of the impedance triangle shifts. Just like in the inductor case, where increasing frequency made the triangle's vertical side grow, in capacitor's case, it does the opposite. The vertical leg gets shorter. This visualizes triangle. So in the diagram, R stays constant, just like before, but X sub C decreases from X sub C 1 to X sub C 3, right? So X sub C 1, X sub C 2, X sub C 3, as frequency rises. And that causes the angle, which represents or the angle theta, that represents that phase angle between the total voltage and current to decrease in magnitude. And you can see that there from the illustration. And it hits closer and closer to 0. So as frequency increases, the current and voltage become more in phase. And this matters because with this triangle, this visualization shows us the frequency response of the circuit. At low frequencies, capacitive reactance is large, and the circuit is more reactive, voltage lags, current more, right? At high frequencies, capacitive reactance shrinks, and the phase angle starts compressing, and the circuit acts more resistive. So this behavior makes RC circuits incredibly useful in filters. For instance, high-pass filters that rely on this principle to let high-frequency signals through while blocking low frequencies. And then compare this to inductors. Think back to our RL triangle. Inductive reactance increase with frequency, causing the angle to rise. Capacitors behave like in a mirror image fashion. Another reason why RC and RL circuits often complement each other in filter design. So next time you're adjusting an equalizer or analyzing a signal chain, remember beneath every sweep of the frequency knob lies a shifting impedance triangle, like a compass needle swinging with each new tone. Stay curious, stay tuned. See applications. So, listeners, if you've been following along, you now understand the math and phasor mechanics of RC circuits. But let's be honest, what really brings a circuit to life is seeing it in action. So let's go and talk about some applications. RC circuit as a phase shifter and low pass filter. So imagine you're trying to delay a signal slightly. Maybe you want to realign it with another or to simulate a time offset. A series RC circuit can do that. And here's the trick. You apply an AC voltage to the input and then measure the output across the capacitor. Remember, where you measure is important. The output doesn't just dip in amplitude, it lags behind the input. And the amount of lag, well, it depends on the phase angle theta, which we covered earlier with our trusty impedance triangle. And the result is a phase lag circuit. And we express it as theta is equal to negative 90 degrees plus theta. I'm sorry, phi is equal to negative 90 degrees plus theta. And this gives us a finely tuned control knob for phase manipulation. You might see it the other way, where phi or phi is equal to theta minus 90 degrees. I like that form better. Um, so look at the waveforms that we see here side by side. Voltage in comes first, then V out follows behind. The delay is precisely what you'd expect from the setup. So it's a bonus feature for low pass filtering. The same circuit is pulling double duty basically. So if you sweep the frequency higher and higher, you'll notice something else. Only the lower frequencies make it out across the capacitor. And so it's a low pass filter. Low frequencies equal high capacitive reactance, so most of the signal drops across the capacitor. High frequencies, you have low capacitive reactance, and the capacitor gets bypassed, so the output voltage shrinks fast. If we want to look at this in practical terms, RC setup lets that's the the bass notes of music say through, but blocks the high treble if you're a musician. I was thinking of a piano, then a guitar, then a bass guitar, and too many instruments jumped through my head. But think about when you go to, which I don't do anymore. Let's say you're going to a nightclub, a discotheque, if you will, right? So just like at a discotheque, there's a bouncer with a very particular taste, right? And let certain things through and certain things out. Uh, I shouldn't say things, people. So let's go ahead and compare this to the inductive circuits. It's always good to compare now that we have covered two different types of circuits, inductive to capacitive circuits. When we talked about our inductor circuits, in our inductor-based low-pass setup, if you remember that, the resistor came after the inductor and the voltage was taken across the resistor. Well, here the layout is reversed, but the goal and the results are the same. They filter out frequencies they don't want, and whether you're sculpting audio tones, stabilizing signals, or prepping inputs for a microcontroller, this RC configuration, it's one of the simplest and most powerful tools in your electronic toolbox. Um, Again, one phase lag at a time, you're mastering analog behavior. So stay curious and keep listening. See applications, part 2. So last time we looked at how a series RC circuit acted as a phase lag generator and a low pass filter. But what happens when we reverse the resistor and capacitor? We've done this before with the RL circuits, right? We enter the world of lead networks and high pass filters. Um, so just reversing components reverses the behavior. And it's just where we're taking the output from. Remember, these things are happening simultaneously within the circuit. So here's the setup. We take our signal V sub in and we run it through a capacitor first, then the resistor to ground. This time we measure the output across the resistor instead of the capacitor. And what's the result? So instead of lagging, the output leads the input. And it's not magic, or is it, right? It's the math of how voltage and current behave with capacitive reactance. So like before, the phasor diagram shows V sub C dragging behind, and that forces V out to jump ahead. And this is your classic phase lead. On the graph to the right, you can clearly see that V out reaches its peak before V in, and that's the behavior we use in signal conditioning. We also use it in timing circuits, and we can use it also for feedback composition and control systems. You're going to take classes of that much later on, and don't forget these concepts. When we're talking about high pass filtering in action, this is where things get spicy. Uh, Again, whatever it takes to make this interesting for you. At high frequencies, the capacitor acts like a short circuit, and the resistor gets the full signal. At low frequencies, the capacitor acts like an open circuit, and voltage out drops to nearly zero. So what are we left with? A high-pass filter, the exact opposite of what we had in the last configuration. So this is a pretty good tool when you want to eliminate low frequency noise. You want to pass along sharp transients, because sharp transients are usually in higher frequencies. Or if you want to detect fast changing inputs. Again, let's go ahead and compare this back to the inductive circuit, the similar inductive circuit, right? And it should sound familiar. We saw the same high pass behavior in series RL circuits when the inductor was placed before the resistor. But in both cases, you're leveraging reactance's frequency dependency. It just happens in reverse for capacitors and inductors. So for inductors, reactance increases with frequency. For capacitors, reactance decreases with frequency. So depending on which type of filter you want, lag or lead, low pass or high pass, you just got to choose the component and choose your position. So just like that, just by reversing those two simple components, you flip the script. Um, that's it. That's power. That's elegance of an analog design. So stay tuned. We've got one more application coming that connects all the dots. RC applications, part 3, or slide 3 of 3, the phase shift oscillator. All right, listeners, let's bring it all together. You've seen how a single RC stage can create a phase shift, but what happens when you chain multiple RC stages together? You get something quite beautiful, an RC phase shift oscillator. And how does that work? In this configuration, you have 3 RC stages, each providing a fraction of the total shift. And you combine them to produce a 180-degree phase shift. And that's the sweet spot needed to satisfy what's called the Barkhausen criterion for sustained oscillation when you combine everything with an inverting amplifier, right? The Barkhausen criterion for stability just says that the loop gain must be unity or greater and the feedback signal must be either phase shifted by 360 degrees, which is practically zero. It's not practically, it's the same as zero or 0 degrees. So we'll talk about that at some other time. And so let's go ahead and break this down. You have each RC pair adds roughly 60 degrees of lag, and you have 3 pairs, and that's where you get your full 180 degrees. The amplifier itself inverts another 180 degrees, and this brings it back to that full 360 degrees. And basically, it's like no net shift. So you have a 0 net shift because it's right back where it started, as far as feedback terms are concerned. So this closed loop is what keeps the oscillation going. No external signal is actually needed. And why does this matter? I'm always wanting you to know why this is important. It's one thing to know how to do the math and get good, get the right answer, but that is a calculator can do that, a computer can do that. You need to understand why, and maybe AI can do this too, but um, we need people like you all to also understand why. So it matters because the circuit, again, it's not only a staple in analog design. The RC phase shift oscillator is simple, it's compact, it's tunable just by adjusting the resistance to the capacitance. You use it for waveform generators, you can use it in test equipment, you can use it in audio synthesis if you're a musician, right? Or if you're going to be like an audio engineer. And here's the thing, it doesn't even need an inductor. So for designs where size, cost, or magnetic interference are of any kind of concern, this circuit is it's gold. Not only gold, it's platinum, right? Uh, oh, okay. So let's go ahead and try to connect this to the earlier slides. So remember back when we covered the RC filters way, way long ago in the before time, um, and we talked about phasor math. So this oscillator is a real world. There I go again. This oscillator is a real world example of all that theory in motion. So you're using phasor relationships to control feedback. You're adding and subtracting angles, just like we did in polar form, and you're engineering a specific frequency dependent behavior to achieve a design goal. So analysis and design, right? So you're doing some analysis and design. If you have those two words in whatever you're doing engineering. So analysis and design. If you can write those, if you can write that in the sentence of anything you're doing, that's engineering. Um, the next time you're tuning a waveform generator or you're simulating a feedback loop, just think about this. You're orchestrating a dance of RC timing and phase alignment that makes the signals sing. And again, that's a wrap on this RC circuit application. Going from filters to oscillators, from phasors to phase shifts, it's all about the timing. And with that said, until next time, stay resonant, pun intended. Parallel RC circuits, sinusoidal response. So welcome back. We're going to dive into the world of parallel RC circuits and introduce or reintroduce three key players. So you can see them here on the slide. Please read along with me. Conductance, susceptance, admittance. Again, this is going to start sounding like an electrical tongue twister, but don't worry. Uh, these are just the natural reciprocals, if you remember, the natural reciprocals of terms that you already know. So conductance denoted by G. Uh, remember, if resistance is how much components resist current, conductance is the opposite, how easily it allows current to flow. It's just a reciprocal. G is equal to 1 over R, 1 divided by R. Or you can also say 1 divided by R at an angle of 0. You're going to see this used often in parallel circuit analysis, and that's because parallel branches add conductance, just like resistors in parallel. So capacitive susceptance, B sub C. This is the reciprocal of capacitive reactance. Capacitive susceptance is the reciprocal of capacitive reactance. By saying that 3 times, right? So B sub C is equal to 1 divided by X sub C. So remember in the series circuit, we work with the capacitive reactance to model inertia of capacitors against alternating current. In parallel, we flip that relationship literally, and we work in terms of how easily the capacitor admits current, right? That leads us to admittance, capital Y, denoted by capital Y. And admittance is just the reciprocal of impedance. So we look at the formula, Y is equal to 1 over Z. So admittance is equal to 1 divided impedance, 1 divided by impedance. In a parallel circuit, admittance becomes your total ease of current flow. So while impedance combines R and X, right? So resistance and reactance, uh, and it does that. We do that in a single triangle series. Admittance does the same thing, but admittance is for the parallel system. The triangle is going to be your new best friend because it's you're going to have headaches if you try to do it any other way, right? And this matters because we're switching gears here. If you remember in series circuits, we added resistances and reactances, but in parallel, we need a new system to account for these things. And admittance is the key here. Much like conductors offering paths for ghosts in those paranormal signal shows that we secretly binge watch, nobody wants to admit. I'll admit it. I watch those ghost shows. I think they're very entertaining. Anyway, um, parallel RC circuits, lost track of where I was talking about, they offer multiple paths for currents, and admittance tells us how easily each one opens up. So go ahead and put that, you can take that to the bank. I don't have any nice cliches here. So just stay tuned. Next, we're going to show you how to combine these admittance phasors, how to calculate phase angles in parallel, specifically for capacitance. We've done this before, but this should be more of a review. And you're going to see triangles, you're going to do some vector math, and that's going to help you get a better crystal clear idea on how current behaves in these branching circuits. Until then, keep your signals sinusoidal. I don't know. There was no pun there at all. Continuing with parallel RC circuits, sinusoidal response. This is slide 2 of 4. We're going to take a continuing look at parallel RC circuits. This time we zoom in on how to analyze phase angles using the admittance phasors. So just to recap, we already defined the three key concepts for parallel circuits, right? Conductance, acceptance, admittance. Conductance denoted by G being the reciprocal of resistance. Capacitive susceptance denoted by B sub C, that's the reciprocal of capacitive reactance, and admittance denoted by Y being the reciprocal of impedance. Let's go ahead and put it all together and go ahead and build the admittance triangle. Imagine a right triangle made from conductance and susceptance. You don't actually have to imagine it, it's up there on the slide. So imagine it or look at the slide. You have the horizontal leg, which is G, the vertical leg, which is B sub C, and then you have the hypotenuse, which is Y. And this forms the admittance triangle, which is the parallel cousin of the impedance triangle that we used in series RC analysis. So mathematically, we write it as Y is equal to the square root of G squared plus B sub C squared. And the phase angle theta, this is going to tell us how much current leads or lags the voltage. We denote that by theta is equal to the inverse tangent of B sub C over G. So notice that this triangle mimics the geometry we used back when we analyzed inductors, except this time susceptance climbs upward rather than reactance reaching downward. And we can interpret the angle here. So if B sub C is larger than G, the current leads the voltage significantly, right? A behavior we expect to see in capacitor-heavy circuits. And here's where things get especially interesting. A large susceptance means a strong capacitive presence, which pulls the phase angle closer to plus 90 degrees. That's the opposite of what we saw in the RL circuits, where inductive reactance pull the angle down. And this is important because the triangle gives us, again, a visual geometric way to think about phase behavior. And another reason I am an advocate for geometry in high schools. I'm not going to get off topic, but they're removing geometry from high schools, and I think that is a engineering crime, right? If you want to have good engineers. Anyway, that'll be the last thing I say about that. I probably mentioned it a few times already in previous podcasts. Anyway, instead of wrestling with complex algebra every time, we can sketch, we can measure, solve. It's especially helpful in AC circuit design and fine tuning. So sorry, I got no ghost stories in this episode unless you count those invisible currents flowing through parallel branches. Anyway, up next in our next, I don't want to say segment, it's just slide by slide. In our next slide, we're going to explore how to interpret this triangle graphically, and we're going to highlight some key coordinate placements. You're going to need to master this for exams and labs. Until then, stay sharp, stay Sinusoidal? I don't know. Stay sharp. Stay. Yeah, I got nothing. Okay, I got nothing. Parallel RC circuits, sinusoidal response, slide 3 of 4, or part 3 of 4 of this little area. So, again, welcome back to the podcast. We're deep into sinusoidal analysis of parallel RC circuits. And one thing, I know this is not a real podcast. I'm just trying to practice my excitement and try to get my podcast voice, going. Today, we're going to highlight some visual insights that make all the difference when interpreting admittance phasors. So plotting the key quantities, let's go ahead and break that down. Remember G, conductance, right? Goes along the positive axis. B sub C, the capacitive susceptance, that travels up the positive y-axis. And this is important because it's a positive J direction. And then we have the resulting admittance denoted by Y. This is the hypotenuse. It forms that classical right triangle. And so we're looking at a phasor triangle in the first quadrant. It's a mirror image of what we saw in the series RL circuits, where we plotted the negative J x sub L on the negative axis. And it's the same triangle structure, but it's just flipped and reinterpreted. So let's look at the angles first. Let's try to get an angle insight. Uh, the angle at the origin first. So it's the phase angle theta, and we calculate it by theta equals to inverse tangent of B sub C divided by G. Nothing new. And this expression helps us figure out how far the current leads the voltage in our parallel RC setup. It's again, I've said before, it's beautiful. It's almost poetic. I've had you all listen to some classical pieces of music, and I've had you visualize an electron moving through a circuit board the way music or a melody moves through an orchestra. It is, and how everything supports each other. It's more than poetic to me. It's I don't have a word for it yet, but it's art. It really is. It's just incredible. It's a life of its own. Like a music composition has a life of its own. How we manipulate the electron and dance with it in a circuit, um, it's very similar to me. Um, anyway, forget about the poem right now or the poetic visualization. In our inductor triangle, current lagged, but with capacitors in the mix, current leads, right? Same math, different orientation. And this is important because when you're sketching this triangle, you immediately see the magnitude of the admittance, right? Denoted by Y. You know how much phase difference exists, and you can predict how your circuit will behave just at a glance. It's like reading the energy dynamics of your circuit off a map. To me, there's a lot more beauty in this, and hopefully, I'll be able to impart that to you uh, sometime in your educational career. But for now, let's do a practical tie-in, right? So when we look at inductors in parallel format from earlier, we saw that there was a similar triangle, but with the negative J x sub L, and now it's pointing downwards. This is why it's important to memorize not just the formulas, but also the quadrant behavior. If you visualize a triangle correctly, this is going to help you stay grounded in labs, quizzes, or when you're debugging real circuits. And that's kind of it for this slide here. Uh, Stick around like you're going anywhere, because next we're going to talk about converting this theory into numbers. We're going to walk through real calculations using parallel RC values. Until then, trace that triangle and remember the imaginary axis isn't just some line, it's a whole new dimension of understanding. And with that said, over and out. I got no more outtakes. Okay, let's continue with parallel RC circuits, sinusoidal response. This is slide 4.4 on this topic. So welcome back to RC Circuit Deep Dive. In this segment, we're finally putting numbers to that admittance triangle we introduced in the previous episode. So let's go ahead and plot it, phasors and all. Right, let's look at the given values. We're working with a parallel RC circuit. R is equal to 1 kiloohms, C is equal to 0.01 microfarad, and we're given a frequency of 10 kilohertz. So let's calculate the conductance and the capacitive susceptance first. And G is easy, right? So G is equal to 1 divided by R. So 1 divided by 1 kiloohm, that's just going to give me 1.0 millisiemens. For susceptance, the capacitive susceptance, it's going to be equal to 2 times pi times f times c. So 2 pi times 10,000 times 0.01 times 10 to the negative 6. And that gives us 0.628 millisiemens. And this gives us the two legs of our triangle. So the horizontal leg, G conductance, is 1.0 millisiemens, and vertical leg, B sub C susceptance, is equal to 0.628 millisiemens. If we want to find the magnitude of the admittance, which is denoted by Y, we need to complete that triangle. So Y is going to be equal to the square root of conductance squared plus susceptance squared. So let's plug the numbers in. Square root of 1.0 squared plus 0.628 squared. We're square rooting that whole thing. And we end up with 1.18 millisiemens. So the admittance phasor diagram places G on the real axis, B sub C, the susceptance, on the imaginary, and Y is that diagonal. This triangle is going to let us visualize how current flows in this particular circuit. Remember that the larger the susceptance, the more the circuit behaves like a capacitor, because we're dealing with capacitor susceptance here. You might remember this triangle looking very, very familiar. Um, and you're right. It parallels it parallels the parallel RL triangle, uh, but just rotate it, right? Because inductive susceptance is negative and capacitive is positive. And again, this is more geometry, and this is why, no, I won't say anything about geometry in high schools, other than it's needed. It's a way to predict circuit behavior at a glance, just by looking at it. So let's compare this to the inductor episodes that we talked about in the inductor episodes. And if you have not seen the inductor episodes, please go watch the inductor episodes. You should have, because that came before this. Uh, but back then, when we covered the parallel RL circuits, we had inductive susceptance, P sub L, and that was plotted downward on the negative J axis. Here, B sub C is plotted upwards on the positive J axis. So it's in the opposite direction. Same math, same rules. We just flip the orientation based on the component's behavior. And I hope by now you're starting to be able to see that since these two are going in the opposite directions, when we're adding those imaginary parts, they start canceling each other out. All right. So this is one of the ways to correct for power factor. If you can start seeing that or thinking ahead. All right. So again, we just flip the orientation based on the component's behavior. And this triangle feels abstract, but practice drawing it, redrawing it with actual values. And if you can do that, and I mean, don't just do it once or twice, do it like 10 times until it's like the back of your hand. You just know exactly what's going to come next. It's going to help you quite a bit for understanding. It's a good visual to help you with calculations. It helps you with building your circuit intuition, and that's what separates the signal chasers from the waveform masters. Some of you all, when you have problems in lab, and I can kind of already tell you by looking at your results what you did prior to that, and you might be thinking, how did you know that? Because I can look at the trends. I can see, well, this is how I do it. All right. So you need to practice the same thing. It'll make you a much better engineer. And one more thing that's not really, it is engineering related, but it's not. Uh, all of these relationships that we're talking about here, they're not just applicable to electrical engineering. They're applicable to um, a lot of other areas in nature that do this, and the other engineering fields. All the math that we study here, there's a mathematical model for something in mechanics, for something in chemistry, or chemical engineering, and so forth. So you're not just learning electrical engineering. If you learn this engineering through electronic engineering, and then you master the basics of this, you can cross over other engineering fields and maybe not work in those fields, but you'll be able to understand them a whole lot better because you've come from a foundation of good engineering. All right, so that's it for now. Next time, we're going to use this very same triangle to sketch voltage and current phasors with real current values. Until then, keep that phasor sharp, keep your calculator close, and not too close. And signing off. I'll see you on the next slide. I'll see you on the other side. That's what I meant. Yeah, actually makes more sense. Analysis of parallel RC circuit. This is a new topic, slide 1 of 2. Okay, students, learners, and waveform chasers, Ghost Chasers. Welcome back to another segment in our RC circuit journey. We're going to go ahead and apply good old Ohm's law, but again, with a twist. We're going to dive into parallel RC circuits where the rules remain very familiar, but the quantities shift names and perspectives. So let's do a quick recap. What changes in parallel? Right? In series circuits, you calculate the total impedance using Z, voltage across components varies, and current stays the same. But in parallel circuits, the roles flip. The voltage across all the components is the same, and what varies? Well, the currents through each path. So here's where the fun begins. We switch from using impedance, denoted by Z, to admittance, denoted by Y. And the equations, we can break them down into admittance is the reciprocal of impedance, so Y is equal to 1 over Z. We can rearrange Ohm's law for admittance to give us I is equal to V times Y, right? So if you know the voltage across the circuit and you know the admittance of a branch, you just multiply to find the current phasor. And that's it. It's that easy. Nothing changes with Ohm's law. These relationships stay exactly the same. The math becomes a little more fun. All right. And this is important because this is how things work in real life. This gives you like a modular tool set. So when you're dealing with different branches, especially with different capacitive reactances, you can analyze each path independently. And it's super helpful in signal processing. It's also helpful for obviously filter design and even in designing like your own oscillator circuits, which you'll learn how to do in other courses, or maybe at the end of this one. In other courses for sure, we build oscillators. But don't forget to take account the phase shift applications for these circuits. So again, always relating this back to a very familiar, similar circuit, so you can have a compare and contrast, and so you can review the other stuff we talked about. The inductor series, right? We're talking about capacitors here, but let's relate this back to the inductor series. Um, we use the same format. We had conductance. We had back then inductive susceptance instead of capacitive susceptance. And we had admittance. But again, all we're doing now is just swapping out the inductive susceptance for capacitive susceptance. And we're treating capacitive behavior instead of inductive behavior. And that's all you need to grab from this slide. And that's all we're doing. That's different from the last time we did it with inductors. If you got that one down, this one is going to be even easier because you've already had practice. So what we're going to do next is we're going to apply this theory to, again, a real example. I promise you we're going to get to a real example. And you're going to see how these phasors come to life when you plug in values and you sketch the results. Uh, again, a calculator does come in handy. Keep it close, not too close. Until then, stay curious, stay steady, and keep the current flowing. All right, let's go ahead and continue with analysis of parallel RC circuits. Again, welcome back, curious minds. In this segment, we're going to be completing the circuit, literally. I say literally a lot, but it's true. Last time we explored how admittance helps us unlock the current distribution in the parallel RC network. We're going to go ahead and apply what we've learned so far. So let's go ahead and start off with the setup. In our previous example, we calculated the admittance components. Remember, so G was equal to 1 millisiemens. That was a conductance. The capacitive susceptance, that was 0.628 millisiemens, right? And then the resulting um, admittance, excuse me, is 1.18 millisiemens. See, even for me, it's hard to keep these words all together. It is a tongue twister. So here's the fun part. We're going to be applying 10-volt source to the circuit. And again, we're going to be applying it to Ohm's law, but in admittance style. And to find the current in each branch, you just multiply admittance phasor by the voltage. So again, I is equal to V times Y. So admittance. Current is equal to voltage times admittance. So we're going to get the current through the resistive branch, current through the capacitive branch, and then the total current. So IR is going to be equal to V times G. IC is going to be equal to V times B sub C. And then the I sub S is going to be equal to V times Y, which is the admittance. And let's look at those calculations. I sub R is going to be 10 volts times 1.0 millisiemens, and that's 10 milliamps. I sub C is going to be 10 volts times 0.628 millisiemens, and we get 6.28 milliamps. And I sub S is 10 volts times 1.18 millisiemens, and we get a total of 11.8 milliamps. Now, Visualizing the current phasors, notice that the triangle formed by the IR, IC, and IS. IR lies along the positive x-axis. I know I'm repeating myself, but again, um, you hear it once, you hear it twice. I don't know. There's a saying about that. Hearing it 3 times, it helps. Yeah, I think it is like hearing it 3 times. But again, IR is always going to be in the positive real axis. That's resistance, always in the real axis. Just like G. I sub C points up along the positive y-axis, so it's going to be a plus J, remember that? Reflecting the capacitive behavior. And the total current, I sub S, that's a diagonal, that vector sum. So this phasor triangle, this is your key tool for circuit visualization. You're not just calculating values, you're seeing how they interact dynamically with phase angles and directionality. And there's a real life link here. This exact method is foundational in designing circuits like passive filters and signal conditioning networks. Anytime you're working with frequency selective circuits, knowing the current distribution, that is platinum. That doesn't sound right. That's gold. We'll say it's gold. And for those following from our parallel RL discussions previously, you're going to go ahead and recall that there's some similarities between that and this. So all we did again was swap B sub L for the inductors with B sub C, and then we flipped the direction of the imaginary axis, and that's the power symmetry in AC analysis. And one last thing to close off this slide. Parallel circuits, like all great systems, are about balance. So you control the phase, the impedance, and the response just by adjusting a resistor or a capacitor for this particular network. And with phasors in hand as a tool, you've got a clear path forward to doing that. So that's it for this slide. We're going to go ahead and look at how frequency starts to shift the playing field. And again, you're not going to want to miss how a simple change in hertz can bend a triangle and realign your signal. This is the professor. Until next time, keep your phasors aligned and your circuit stable. Did that rhyme? Kinda. You with phase angle of parallel RC circuits, right? It's time to look at what happens to a parallel RC circuit when you start turning the frequency dial up. And spoiler, our phasor triangle doesn't stay still, it bends with the beat. So let's look at the formula behind the phase. If you can recall or remember from our earlier chat that capacitive reactance X sub C is inversely related to frequency, right? If you remember X sub C is equal to 1 over 2 pi FC, well, susceptance B sub C is the reciprocal of that reactance, which means it increases with frequency. So it's directly proportional. So B sub C is equal to 2 times pi times F times C. So as frequency increases, B sub C increases, and since I sub C is equal to voltage times capacitive susceptance, or B sub C, your capacitive branch current I sub C increases too. That's a lot of variables and a lot of words that sound the same here. So uh, replay this part over and over if you want to. Uh, let's talk about the phase angle. So not just some number. It gives you a visual cue. If you look at I sub R from the resistor's point of view, that stays steady. It's again, I sub R is on the horizontal real axis. Resistor, real axis. It's always going to be on the real axis. I sub C rises up, it points vertically on the imaginary axis, and the total current I sub S becomes the hypotenuse of the triangle. And the theta between I sub R and I sub S, that theta between those two, that's going to tell us the phase relationship. Because I sub C is growing, this angle theta also increases. At high frequencies, the total current leads the voltage by a greater amount and greater amount. So um, that's the reverse of what we saw in the inductor. It's always going to be the reverse of what we saw in the inductor. Uh, Remember, where current lagged more with frequency. Well, capacitors are kind of like the eager types. They respond faster as frequency increases. So a nice little frequency response reminder. Uh, why did this matter then and why does it matter now? Because when you're doing AC analysis, the phase angle controls how signals add, cancel, or how they get filtered. Looking at this triangle, the relationship between I sub R, I sub C, and I sub S, this is your key or your tool to see or visualize how reactive power shifts with signal speed. It's also the backbone of frequency selective filters like tone control circuits or noise cancellation systems. And let's go ahead and wrap up this slide with one point, maybe two. Next time you're sweeping a signal through your circuit and you notice a shift in behavior, now you might have not done any frequency shifting yet, but you will. Remember that the triangle never lies. Did I say that correctly? The triangle never lies. So if you crank up the frequency, you're cranking up I sub C. Rotating, that rotates the phasor triangle and it reshapes how current flows. Again, this is the professor reminding you, don't just calculate your phasors, actually visualize them, feel the shift, and I'll catch you on the other side. Oh, that's good. Catch you on the other side. Moving on with equivalent series and parallel RC circuits, what if I told you that every parallel RC circuit has a twin, counterpart in the world of series circuits? At least for a particular frequency, a given frequency. And that's true. And that's exactly where we're headed today. So you have an equivalence at a given frequency. And why do we care about this? Well, because when you're analyzing or you're designing circuits, sometimes it's just easier to work in series, and other times it's actually easier to work in parallel. And it just might make more sense to work in a parallel. And the trick is knowing that the behavior of these two topologies can be matched. So at a specific frequency, you can take a parallel RC network and you can create a series version that behaves the same in terms of its impedance, magnitude, and phase angle. You're going to do a lot of this conversion later on if you're in the bachelor's degree program when you do circuit analysis. You'll be learning how to convert between parallel and series circuits or making an equivalent circuit. So let's get back to the impedance triangle. On this slide, you see that the geometric shortcut helps you convert the following. So the hypotenuse of the triangle being the total impedance. Always remember the horizontal side is the equivalent resistance. So uh, R equivalent is equal to the impedance Z times cosine theta. And the vertical side is the equivalent capacitive reactance. So X sub C equivalent is going to be equal to Z times sine theta. The triangles, it's not just geometry. It's not just something to look at. It's a translator between parallel and series circuits. And this is like a basis of how it works. So let's say you've analyzed a parallel RC circuit and you found the following. You found the total impedance, Z, you found the phase angle, theta, but you want a series circuit to behave the same way. So you plug those values into the equation above and voila, I know a little French. I think that's French. Then you convert the reactance and resistance from one form to another without redrawing your entire analysis from scratch. So it's like a conversion, right? So at this point, you just convert and you get the equivalent circuit. Think of it like the mirror world version of the impedance triangle that we explored earlier, like the RC and RL segments. I want to say, think of it like the upside down, but again, these videos are going to be on YouTube. Somebody will get upset that I made a Stranger Things reference, and they'll copyright me for it. I have no idea. But for inductors, just back to the subject. So we rotated the triangle clockwise. That was for inductors, but for capacitors, um, we're in that downward pointing triangle that still holds the same rules. And this is another reason the phasor triangle is your best visual tool in AC circuit design. You may not have a lot of homework problems that deal with this, but just practice converting or drawing these phasor triangles. So again, I won't spend any more time on this slide. Let's just wrap it up. So if you're working in lab, you're sketching out a filter or like you're reverse engineering a design, this tool is going to help you swap perspectives and it's going to help you simplify the math. All right, so that's it for this slide. This is the professor saying, the circuit may change as closed, but its behavior stays the same if you know the angles. Catch you on the next one. Next slide. All right, let's look at the RC puzzle box. All right, so you ever play with one of those Japanese puzzle boxes and each panel is like a mystery and you can't open it unless you move every piece in just the right order? And that's what today's circuit feels like. It's a blend of series and parallel elements that make up a series parallel RC network. I'm sorry, I'm chuckling a little bit because I put one of these three-dimensional wooden puzzles together. My brother showed up and he thought it was one of those puzzles that you have to take apart and there's a trick to it. And of course, he took it apart right away. And he says, "Well, that wasn't so hard. I took it apart right away." And I said, "No, the goal was to put that puzzle together and it took a long time." Uh, so that just kind of popped in my head. Uh, Long story short, he never put my puzzle back. Anyway, let's get back to this. Let's crack this open. So you got two zones here. You got the green and the yellow, and in the circuit diagram, you're going to notice the two color-coded sections. The green box, that's a series connection of a resistor R1 and a capacitor C1, and the impedance here is pretty straightforward, right? Z1 is equal to R sub 1 plus J X sub C1, right? The first capacitor. And then you got the yellow box. This is the one that's a parallel combo of R2 and C2. So we need the parallel impedance formula. So Z2 is equal to R2 and, sorry, the second resistance time, capacitive reactance, X sub C. Again, it's a classic mix. Think of it like you can think of it like a crime scene where you get both a fingerprint and a footprint. I don't know if that actually helps, but they're both limbs. I'm trying to make something where they're both something similar but yet different. Again, we just need to use different tools to analyze each of those. And the next thing is we got to combine those two. So once you've calculated both impedances for Z1 and Z2 for both of those boxes, then you can just simply add them together, where Z total is equal to Z1 plus Z2. But don't forget that you're working with phasors here, not just magnitudes. So that means keep the angles in play, convert to rectangular or polar form as needed, depending on the math you need to be doing, and be cautious with the signs and the quadrant placements. This is where all the training from all of the earlier modules pays off here. So let's look at the tools that we actually put in our toolkit from the previous podcasts. I'm kind of iffy about using the word podcast as I do this. Um, I just got to get comfortable with thinking that I'm doing a podcast style lecture. Let's just go ahead and review what you're expected to bring into the problem. So you have reactance for capacitors. Again, the formulas you should know by now. X sub C is going to be equal to 1 divided by 2 pi FC. You have complex impedance handling from rectangular to polar form. Then you have phasor addition rules. So you have the real plus the real, imaginary plus imaginary. Remember, likes to likes. Um, and you're going to use all of these tools to navigate this maze. So let's do a real world reflection. Again, you all know I have a hard time saying real world reflection. So again, in real design work, you mix these RC circuits up often, like with audio filters, timing networks, signal shaping applications. And they're powerful because they give us the best of both configurations. You can get a sharp control of frequency and flexible response profiles of the circuits. And that's pretty much it for this slide. I just want to wrap it up by saying if uh, you have a pure series and a pure parallel RC circuits, they're like individual chess pieces, right? Series parallel combinations are like an entire strategy. So one piece doesn't win the game. It's how you kind of combine them. Um, I'm not sure if that was poetic advice or whatever, but hopefully it helps. I have to rephrase that somehow. Again, this is the professor saying, master the pieces and you control the board. Now, that was good. Through the power triangle. All right. So you are all going to be like detectives or sleuths today. When I say sleuths, I know it's hard to understand what I'm saying. Sleuths, sleuths, detectives. All right. So we're going to be reviewing a familiar scene, but we're looking at it from a new angle. Literally. I got to stop saying literally. Again, it's time to revisit our trusty, rusty triangle. But in this case, we're going to look at power in the RC circuit. And let's go ahead and break this down. So if we go from impedance to voltage, back in a previous lecture, we mapped out an RC impedance triangle where we had resistance that was equal to 1.2 kiloohms. We had the capacitive reactance right? X sub C equal to 960 ohms. We're using the same numbers over and over again so that you're not so focused on the mathematics or the arithmetic, but more focused on the concepts. And we had that resulting impedance, Z being equal to 1.54 kilo ohms at an angle of negative 38.7 degrees, right? So we're keeping the numbers the same. But now with a current of 10 milliamps in RMS. All right, so what we do is we multiply that impedance triangle by the current to produce the voltage triangle. V sub R is going to be equal to I times R, which is 10 milliamps times 1.2 kilo ohms. That gives me 12 volts. That's one leg of the triangle. V sub C is I times X sub C, which is 10 milliamps times 960 ohms. That's 9.6 volts, which is the other leg of the triangle. And then we can do the total voltage phasor, which is V sub S, and that's going to be equal to I times Z, the impedance, which is 10 milliamps times 1.54 kilo ohms, and we get 15.4 volts at negative 38.7 degrees. Now notice how the shape of the triangle stays the same, but it's just scaled by the current. Right? Scaled, S-C-A-L-E-D. Right? Sometimes I know that it's hard to understand some of the words I say because I may be talking too fast. But that's the beauty of the phasor multiplication. And it's important because this triangle shows how power is distributed in your circuit. So you got the real axis, and that gives us the resistive contribution. You got the imaginary axis, and that shows the reactive contribution from the capacitor. Again, this is just RC. Wait till we get to RLC, and you're going to have two contributions from the inductor and the capacitor. That is going to be crazy fun. But this is just RC. So again, the angle still tells us about the power factor and how much current is leading voltage. So this triangle gives a voltage-based snapshot of where your energy is going. Let's do a callback to the inductors, if you can remember that. We covered the RL circuits. We use that same triangle, but with an upward reactance vector for the inductor. Well, with capacitors, by contrast, just flip the triangle downward, and that gives us a negative phase angle. So in a way, this isn't just another power triangle. It's a mirror image of the one you saw before. And that's about it for this slide. Again, a final thought on this slide. Just remember, if you multiply your impedance triangle by current, you're not just scaling the lines, you're building a map of energy flow through the circuit. So this is how engineers see beyond wires and symbols into the soul of the signal. Again, this is Professor Vasquez signing off with one line. Power doesn't lie, it just rotates through the triangle. Right? That's not poetic or anything, but still, it's true. Power that packs a punch. So welcome back, curious minds. Today we're adding a new triangle to your analytical toolbox. And this one doesn't deal with voltage or impedance alone. Again, it deals with power. Not new, it's just power with RC circuits, but it's new for this lecture. Let's go ahead and step inside the triangle of the apparent, the reactive, and the true power. We're going to build the power triangle, and here's how it flows. So we already had our voltage triangle that we discussed earlier. The voltage for the resistor was 12 volts, voltage to the capacitor was 9.6 volts, voltage of the source was 15.4 volts at negative 38.7 degrees, right? So we're going to go ahead and multiply each of those by the RMS current one more time, because remember, voltage times current, wait a minute, power, I squared R. Yeah, so I'm sorry. We started off from the impedance triangle, I squared R. So R, think of R times current times current. So we started off with impedance, we multiplied it once times current, and that gave us voltage. We multiplied by current again, that gives us power. So hopefully you see that relationship that we've been following through for the last couple of lectures. And we're going to multiply it by an IRMS of 10 milliamps. And so we get true power, again, the horizontal leg of the triangle. P sub true is going to be equal to V sub R times I. So that's 12 times 10 milliamps. That's going to give us 120 milliwatts. We have the reactive power. That's the vertical leg of the triangle, P sub R. So that's going to be V sub C times I. So 9.6 times 10 milliamps. That's going to give us 96 millivars, millivolt amp reactive. And then we have the apparent power, which is the hypotenuse of the triangle, or P sub A. And that's the voltage source times I. So it's 15.4 times 10 milliamps. And that gives us 154 millivolt amps. And the result, well, you got this beautiful power triangle with apparent power of 154 millivolt amps at negative 38.70 degrees. And what this tells us is that this triangle isn't just like some academic exercise. It actually tells us quite a bit. So how much power is doing the real work, right? The true power. How much is sloshing back and forth without being used? That's that reactive power, P sub R. And then how power efficient the system really is via the power factor. We've talked about the power factor before, but just like with RL circuits that we did prior, if this triangle were flipped upward, you'd be dealing with an inductor. But RC versions, they dip downwards. So showing that voltage lags behind current is what we need to visualize in this triangle. It's pattern recognition in some way. So there is a sequence though. So you multiply impedance triangle by current, that gives you the voltage triangle. You multiply the voltage triangle by current one more time, that gives you the power triangle. And each time the triangle shape remains constant, but the scale and the units change. That's all. Right? So wrapping this up, the power triangle is your forensic report of an RC circuit. It shows you not just what's happening, but it shows you why it matters in terms of energy. And this is per the professor. Sorry, that's my fun name. The professor inviting you to draw the triangle one more time and let it speak volumes about what your circuit's really doing. I would say go back to these slides and draw these triangles without referencing the slide. So draw the triangles and go back to the slide, look at it back and forth to understand it, and then be able to do it without looking at the slides at all. Right? So until next time, stay grounded. That's a good one. Okay, so this has been a very long lecture. This is 53 slides for this PowerPoint, but hopefully you've been keeping up and you've had the resilience to hang on. So let's talk about power. What is or power factor? What is it, right? So again, we're going to be repeating what we talked about with inductors. So let's go back to series where we uncover the secrets beneath every resistor and capacitor. You've seen impedance triangles, you've walked the voltage vector path, you've climbed the power triangle, but now uh, we're going to scale it all. That's where the power factor comes in. So what is power factor? And I said it similarly back then. I'm going to say it again. It's deceptively simple. The power factor, right, denoted by PF, is equal to cosine theta. And we derived how we got that the last time. And theta is that phase angle between the voltage and current. So that means that the power factor tells you how much of your apparent power is actually doing useful work and how much is just like taking a reactive joyride through the circuit. Um, there's a range of this reality. So if you have a power factor of 1, that's perfect. Voltage and current, they're in sync. Every bit of power goes into doing something real, like lighting a light bulb, charging a battery, heating your toast. I'm saying that because I need to get a toaster because I really like toast. I don't have a toaster or a toaster oven. Sorry, got off topic there. But if I repeat it to myself, I won't forget to go buy a toaster. And then a power factor of 0, that's a no-no. It's all reactive. So your system is slinging energy back and forth like a ghost in the attic. Nothing's being used. Um, nothing real is happening. So your mix of true power and reactive power, right, is producing nothing. The analogy is like imagine a horse that's pulling a cart. The more aligned the horse is with the direction of the cart, the more effective the pull. And that angle, that's your theta. So power factor, it tells how much of the horse's energy is actually moving the cart forward. And if we relate this to an RC circuit, especially at lower frequencies, the capacitor causes the current to lead, and that gives you a non-zero theta, and that means that your power factor drops. You're like, oh, why should I care? Because lower power factor means more apparent power required for the same amount of real work. And that leads to larger components, higher currents, and wasted capacity in power systems. The same thing we mentioned before when we were doing RL systems, right? The general abstract understanding of this is the same. So in industry, if you're looking at utilities charging you for poor power factor, yeah, that's not good. Um, so you get billed for wasted power that you're not actually using. It's not going to do anything that you need. and they're very inefficient. So you don't want that from your engineers and your power distribution networks, right? So let's wrap up this slide. Next time you analyze an RC circuit, don't just stop at voltage and current. Look at the power factor. It's the efficiency report of your entire AC operation. Think about your utilities if that helps, right? 'Cause when it deals with dealing with utilities, you're thinking money that you're spending. And so again, if you relate it to that, that might make it stick. Every time you go home, it'll be real to you, right? Cosine theta, remember it's more than math. It's your circuit's truth theorem. So it'll let you know how much is real and how much is apparent. All right. Till next time, this is the professor reminding you, don't just build the circuit, understand its soul. I want to thank you for hanging on this long. This has been a very long presentation. Let's go ahead and continue with the mystery of apparent power. So we dive into what appears real, but we might not be. So we might not, again, I'm not going to give you another ghost reference, but maybe just a whisper of one, right? So we're talking about apparent power, right? The full package, the whole triangle, not just the part doing the work. What is apparent power? Apparent power, right? We label it as P sub A with a little a, and this is a total power supplied by the source to an AC circuit. It's measured in volt amperes, VA, right? And here's a trick to this: not all of that power actually gets used. Apparent power is made up of true power, P sub T or P sub true. We measure that in watts. Again, this is a review. And again, this is a power that actually performs useful work. We also have the reactive power, P sub R. We measured that in VARs, the volt ampere reactive. And this is the energy that just oscillates back and forth, right? It doesn't do anything. And imagine that you're carrying like a heavy box, and that's the apparent power, P sub A. And part of the effort is P sub true, which helps you move forward, and the other part is P sub R. It's just like balancing the weight side to side so you don't fall over. You know what a good example of this is? There's this backpack that I saw. I want to say infomercial, but I don't know if that's the right term anymore. And where there's an oscillation that's moving um, with the backpack so that the person who's running forward, they're not losing forward momentum. And so that oscillation or that movement of the backpack where it slides up and down, that's kind of like when you're trying to balance out, let's say, inductive to the capacitive, right? You use your capacitive power to counteract the inductive so that your reactive power is less, right? So I got to find that video. But if you all know what I'm talking about, look that up. That's sort of like a mechanical version of what we're talking about here. Um, the backpack being able to react is kind of reacting to the person moving up and down. So um, it's not minimizing the true power of the person actually running with the backpack moving forward. That's actually a pretty dang good example. I've got to find it for lecture. So, like we saw in the impedance triangle, you have apparent power, and that's the hypotenuse. The base is P sub true, the vertical is P sub r, and together they form a right triangle, again, P sub a at a slant, and that angle theta, the same phase angle we discussed in the last section. And this is important because when engineers, like they size generators or transformers and motors, they don't use watts. They use VA. They use volt amps. And why would we do this? Because those devices have to handle the total power, both the real and the reactive power. So even if only a portion of it goes into useful work, um, you have to account for it. So that's why transformers, they list that rating of, let's say, 1 kilovolt amp VA instead of 1 kilowatt. And if you go to your cabinet, parts cabinet, and pull out any of those transformers, I promise you, they have that label on there. But the bottom line is apparent power, P sub A, or in volt amps, that's going to equal the total energy flow capacity. True power is in watts, and that's the actual energy that's consumed. And then the reactive power, to repeat one more time, is in VARs. That's the energy that's cycling back and forth. And yes, your company, your power company, they might be charging you for apparent power. You're billed for carrying the box, right? Build as in you're not build as in building something, build as in billing, right? Uh, so that's part of the bill, not just what's inside of it. And I think we're almost done. Again, this is a professor. Stay sharp. Keep tracing those vectors. Power doesn't always tell the truth unless you know how to read it. Again, this is a professor signing off. Until the next waveform. We've reached the part of our podcast where we kind of do a little review of the key terms that we discussed. And let's go ahead and go with the first one, which is complex plane. And that's an area consisting of 4 quadrants on which a quantity containing both magnitude and direction can be represented. The next selected key term is real number, and that's a number that exists on the horizontal axis of the complex plane. The next one is imaginary number. It's a number that exists on the vertical axis of the complex plane. And so if you've ever wondered, like in algebra, when they say imaginary numbers, what is it? What is it? What is it? Now you have a better contextual understanding of how imaginary numbers and real numbers work and how we use them in engineering and why you had to learn them in algebra in the first place. Okay, the next key term is rectangular form. This is just one form of a complex number. Sorry, I should be reading the definition. One form of a complex number made up of a real part and an imaginary part. So the rectangular form is both real and imaginary. Continuing with the selected terms, the next one is polar form. That's one form of a complex number made up of a magnitude and an angle. So go ahead and visualize what that looks like. The next selected key term is impedance, the total opposition to sinusoidal current expressed in ohms. And the next term is capacitive susceptance, or B sub C, the ability of a capacitor to permit current. That's the reciprocal of capacitive reactance. The unit is in Siemens. Following with the selected key terms, the next one is power factor, the relationship between volt amperes and true power or watts. Volt amperes multiplied by the power factor equals true power. The next key term is filter, a type of circuit that passes certain frequencies and rejects all others. And the next term on this slide is frequency response. In electric circuits, the variation of the output voltage or current over a specified range of frequencies. And finally, the quiz review. So question 1. Complex numbers can be expressed in polar form. The angle is measured from the what? Positive real axis, negative real axis, positive imaginary axis, or the negative imaginary axis. Go ahead and pause the video now. All right, if you come back, the answer to this one is the positive real axis. Question number 2. If a phasor that is expressed in polar form has an angle of negative 45 degrees, it is in the what or where? Right? A, the first quadrant, B, second quadrant, C, third quadrant, or D, fourth quadrant. Go ahead and pause the video now. Okay, if you're back, the answer to this one is D, the fourth quadrant. Question number 3. To multiply two numbers that are in polar form, you do what? Or which of the following? A, add the magnitudes and add the angles. B, multiply the magnitudes and add the angles. C, add the magnitudes and multiply the angles. Or D, multiply the magnitudes and multiply the angles. Go ahead and pause the video now. Okay, if you're back, the correct answer was B, multiply the magnitudes and add the angles. Question number 4. Given the impedance phasor diagram of a series RC circuit, you could obtain the voltage phasor diagram by doing what? A, multiplying each phasor by the current. B, multiplying each phasor by the source voltage. C, dividing each phasor by the source voltage. Or D, dividing each phasor by the current. Go ahead and pause the video now. All right, if you're back, the correct answer was A, multiplying each phasor by the current. Number 5. If you increase the frequency in a series RC circuit, which of the following is true? The total impedance will increase, the reactance will not change, the phase angle will decrease, or none of the above. Go ahead and pause the video now. All right, if you're back, the correct answer is C. The phase angle will decrease. Quiz question number 6. In a parallel RC circuit, the capacitive susceptance is plotted on an admittance phasor diagram along the what or where? A, positive real axis, B, negative real axis, C, positive imaginary axis, or D, negative imaginary axis. Go ahead and pause the video. Okay, if you're back, the correct answer is C, positive imaginary axis. Number 7, quiz question. Given the admittance phasor diagram of a parallel RC circuit, you could obtain the current phasor diagram by doing which of the following? A, multiply each phasor by the voltage. B, multiplying each phasor by the total current. C, dividing each phasor by the voltage. Or D, dividing each phasor by the total current. Go ahead and pause the video. Okay, thank you for coming back. The correct answer here is A, multiplying each phasor by the voltage. Question number 8. If you increase the frequency in a parallel RC circuit, which of the following is true? A, the total admittance will decrease. B, the total current will not change. C, the phase angle between I sub R and I sub S will decrease. Or D, none of the above. Go ahead and pause the video. Thank you for returning. And the correct answer is D, none of the above. Question number 9. The magnitude of the admittance in a parallel RC circuit will be larger if what? A, the resistance is larger. B, the capacitance is larger. C, both A and B. Or D, none of the above. Go ahead and pause the video now. Thank you for returning. And the correct answer is B. The capacitance is larger. Finally, for this very, very long presentation, quiz question number 10. The maximum power factor occurs when the what? A, circuit is entirely reactive. B, reactive and true power are equal. C, circuit is entirely resistive. Or D, product of voltage and current are maximum. Go ahead and pause the video now. All right, thank you for returning. And the correct answer here is C. The circuit is entirely resistive. Go ahead and check your answers here with what you chose on the previous slides. Remember, don't just know what the right answer is. It's also good to know why the wrong answers are wrong. If you know that, you'll master this material.